As we get into more complicated problems, it's important to have a good process to follow for designing software solutions to those problems. One common software development model is the one that I'll show here, where we start out by looking at the details of the problem itself. What is it that we're trying to solve? What task are we trying to do with a computer? What is the actual need? Then, to determine some specifications based on that problem that we're looking at. From those specifications, then we can create a design. And that design doesn't have to be specific to a particular programming language. It should have very little to do with actual lines of code at that level. And then we work, once we have a general design, we work to implement that design in an actual programming language. We test and debug the program once we've written some version of it. And as we test it, we can find errors and fix those. And then even once we have what we think of as a fully functioning version of our program, we might still have to do work over time to maintain that program if it's being used still. So, stepping back, we have to understand the problem that we're needing to solve. And when we say problem in computer science, that doesn't necessarily mean anything bad is happening or anything like that. The problem could be as simple as, I really want to be able to quickly look up my recipes. And that's a problem you have because you don't already have a tool to meet the need that you have in that situation. It could be something like, I want to navigate from here to my parents' house. And so that's a problem that's being solved by something like Google Maps, for example. And to write software well, you really need to understand the details of that problem. What are the features that are important? Are speeds as you drive important to that navigation problem? Or do you really just want any path? Do you have some limitations on what's going to be available to you in terms of money or gas or things like that you need to take into consideration? And as you think more about the problem, you'll start to narrow down to what features are actually important to you. And because you could grow a problem to be infinitely large if booking a flight and paying for tickets for it were included in my navigation system, that becomes a bigger and bigger problem as I go. And so I need to think about what could be the wider terms, and do those make sense? Do I really need to solve that big of a problem? And what are the narrower versions? And do those make enough sense that it's worth me writing my piece of software just to handle those? And then once you've got that range of what you actually need to consider, then you have to think about different possible cases. Circumstances where the need is just not possible to meet. There is no path from where I am to where I want to go that gets me there in time, for example. And so I will have to eventually think about how my program would handle those. For now, all we're thinking about is the problem itself. What are cases that I might see? And so I have to think about those different possible cases to lead me into finding a specification. A specification is thinking broadly about what your program will do. So my program will find paths from location A to location B and calculate the time that it would take to get there, for example. Or my program will allow users to search for recipes that are already known in a recipe book. And from the problem that we figured out the details of, then we come up with things like inputs and outputs. Someone might input the 2 locations that they want to go to and from, and how long they have before they need to get there, or what time they need to get there. And you would take those and turn those into specific possible inputs. And that allows you to think about cases. Often when people are doing this level of thinking about software, they're thinking about use cases, how people will actually use the software that is being thought about and being created. So users will use this by searching for a recipe, and maybe they will sometimes have a recipe they really like and they want to bookmark it and keep it for later. And so these provide us with details of what the features of our program will be, not the code and not the specifics of how it will achieve those features, but just what the features are. What are the use cases that someone might have in their needs to use this program? You may sometimes revisit this specification step if you discover that you need additional possible inputs. Your users had more things in mind than you might have thought up originally, especially once you get to the point of implementing that software. So once you have a specification, and again, the specification deals much more still with the problem itself. So once you have a specification of the uses that people might have for your software, then you start to create a design. And the design gives you some of the how it will work. This is the level at which you might start to create, diagrams of the flow between different parts of your program. This is the level at which you might start to think through what are the important function names that you're going to need, and generally what will those functions do. Again, still not touching code, but this might be the point where you start to write some pseudocode for an algorithm, for example. Pseudocode is where we write things sort of step by step that look a little like code, but they're not particular to any programming language necessarily. They describe what a program could do and don't handle all of the little implementation details of the specific language and the specific program as it will be written. Because once you have a design, then you start to implement the design. If that design is written well, then your job is primarily translating that design into the computer language that you're going to be using. And also, if that design is written well, you should theoretically be able to translate that design into any programming language. This is how people can take the design for a piece of software that worked on a mobile device and then implement it in a different language and a different framework to work on a desktop or that sort of thing. So implementation is often what programmers get very, very heavily focused on, but implementation can also be much, much easier if you've already put together a very clear design that gives you the structure of what you're wanting to look for, and then the programming is just putting the details inside of that structure and making it work step by step. Once you have some implementation, and it does not necessarily have to be a full implementation of the whole program as it will be at the end. It could even just be an implementation of a function, a piece of the program, for example. But once you have some implementation, then you want to test and debug the program. So you try out your different inputs, the things that you had thought up as your use cases. You program those in to run through them, or you click things and you do whatever you have to do in the program and run through them to see that you get the expected outputs, the expected results. When you're testing, you also want to think about the corner cases or the weird situations that you might run into. A user, for instance, tries to enter 3 decimal places for a value that was supposed to be money. Well, that's an unexpected case in the sense that you don't really want it, but it's a realistic case that it might come up, it might happen. Things like negative values, zeros, someone clicks the wrong button at the wrong time. These are corner cases, and you want to try to test your program out and make sure it handles them well, because you don't want your program to crash on someone. You want your program to be smooth. You'd much rather have it display a notification to them that they shouldn't have put 3 decimal values for a dollar amount, rather than the program accepting that value and getting wrong calculations later, or erroring and crashing altogether and losing whatever the person has been trying to work on. Some bugs will manifest as error messages. Sometimes your program will have an error, like an index out of bounds error, or value errors. I think we've seen so far probably in Python. So sometimes you'll be running your program with different inputs, and you'll actually get an error message from Python, from the operating system, from the programming language, something like that. And those can be very helpful because they tell you that your program has something going wrong, and you can go back and debug it. But it's also important to remember that not all errors come with error messages. For instance, you might very kindly print out to a user that their income this week that their paycheck this week is a negative amount because you did your calculations wrong. That probably won't pop up an error message, but I bet that your users will be a bit frustrated with that situation arising. And so you really want to make sure not just that your program runs without error messages, but that the outputs you get from your program, the results of your program, and the progress your program makes as it's executing all make sense. And that's where your design and your specification can be so useful, because you can turn each of those pieces of the specification, those use cases, you can turn those into tests. You can write code that tests them, or you can follow the process of that use case and use it as a test and make sure you get the result that you expected to get. And then once you've written your software, you feel that it fully meets its specification, maybe you release it out to users to use, then you have to maintain the program. If you want to have happy users, if you want to have that software continue to be useful to people, then you have to maintain it. Many software programs don't follow through on this step. Somebody just posts some code and lets it sit up there, and 8 years later, if you try to run it on a new operating system or with the current version of that programming language or with the large data sets that now exist that didn't exist 8 years ago, it crashes. It doesn't work. It doesn't do the job. It's useless at that point. And so maintaining a program is a really important step too. As your users use the program, they'll find issues that you didn't realize were there, either bugs in your code that your tests didn't hit, or cases that they yet again didn't really communicate to you were needed, or for instance, if you're writing an Android application and the Android operating system gets a new version released, they might remove some of the functionality you were using before, or they might add new functionality that, if you used it, would make your program way more effective. And so it's important to continue to maintain your program after you've finished implementing the basic specification. And it's also important to understand that many of these are sort of cyclical. There's a cycle to many of the steps that we've talked about here. For instance, after you've created a design and you implement that design and start to test it, you may find problems so big that they require you to redesign the program. And you should come back to your design documents and change them so that they reflect what your program is actually going to do. Make new versions of that design or whatever. Because What programmers often do is as they test the program, they find something is very, very wrong. And so rather than changing the design documents, they just rip apart the program and change it altogether, how it works at what should be a design level. And now all of those design documents, all of the thought that they put into that previous design and the work they did to actually record it somewhere is useless. And if you are working with someone else who may take on your code later or who you're sharing parts of the project with, they might have been relying on parts of that design that now no longer match the program. And also, it's much more likely that you'll make a mistake that invalidates other parts of the design of your program if you're just hacking apart the code, trying to solve big problems rather than stepping back to your design, thinking through all the parts that you had originally thought through, and finding the pieces that need changed, replaced, redesigned. And similarly, as you're maintaining the program, you're going to have to be testing and debugging. And you may even find maintenance needs that are so big that you have to come back and redesign the software and come back down through the steps again. A few other notes on ways that you can make good software are that you really ought to make your code readable and make it make sense to someone who's looking at it, you or someone else. So speaking of naming things, for instance, variables or functions, there are a wide range of things that you can name a variable or a function. You can name them Bob, or you can name them all X and Y and A and B. But that does not mean that that is what you should do. So strictly speaking, you can name a variable in Python beginning with either a letter or an underscore, and you can include letters, digits, and underscores for the rest of the name, so long as it's not a reserved keyword like return or def. You can't name a variable those. But again, that leaves you a wide range of possible things you can name a variable, not necessarily what you should name a variable. I myself have inherited code from another programmer on multiple occasions who named things in their program stuff like window 1, window 2, button 1, button 2, button 26, function 1, function 2. You can name all of your stuff simple names like that, and they will be completely useless to other programmers who see your code and probably useless to you at some later point because you're going to have a very difficult time remembering what the different parts are and how they go together. So when naming a variable or a function, you should give it a name that clearly describes what it represents, or in the case of a function, what it does, especially if it's a variable that's used in more than one place or a function that's used in more than one place. Certainly your loops, if you want to name your loop variable I, and that variable is not used in any other places, and it's really just used to step through the range 0 to 10 or something like that, that's fine. Of course, a short variable name is very helpful in some situations. But if it's going to actually mean something, if it is the maximum size of a window, if it is the number of cups or the number of gallons, give it a name that actually means something. You definitely should not use the name of something else that already exists, like print. You can in Python run into problems where you accidentally replace some built-in functionality if you use names that you know you're going to need for instance, printing stuff out. You should also use a consistent style of naming. There are multiple different options of styles that people might suggest to you. If you really want to start an argument between programmers, then bring up whether they should use uppercasing between words or underscores between words in their variable names. For our purposes, either of these is fine as long as you're consistent in it. You don't want to be switching around between different styles because then you won't be able to remember which style you used for which variable. So find a style that works for you or a style that works for you and the people that you're collaborating with and stick with it. Another thing that you can do to make your code more usable to you and to other people is to add comments or documentation to your code. So in Python, you can put a £, or a hashtag if you prefer, before or at the start of a line, and that causes the programming language to ignore it. It's just for people. It's sort of a label or an explanation, and it will not be executed. It can't be executed. So these 2 lines here are comments in Python. And you could use them, for instance, to explain that a particular variable should never have a negative value. You could use it to explain what a function actually does. You could use it to describe what your idea was for this particular loop to handle. There is another way that you will sometimes commonly see, and that's a multi-line string. And it is actually technically a real string in Python. People will often put these multi-line strings at the just inside a function or just inside the definition of some other large block of code because it can be used for multiple lines. It also can be used by Python systems to create neat web pages that document your code, like the ones that you'll find for, say, the random library or the math library in Python. You can write strings like these for all of your functions, and then there are good tools for turning those into a web page that documents your code so that other people could understand what your code is supposed to be doing as well. For our purposes, it doesn't really matter if you use comments or you use doc strings, but you really should include some stuff to describe what's going on in your code. You use comments and doc strings to make your code easier for a human reader to understand. And as a general rule, it's good to make your code as understandable as possible, regardless. And comments can be one way to do that. A thought experiment is to think about which of these 2 is a better situation to choose. Using an unclear variable name, like just W for something, but explaining it in a comment where you declare that variable, where you create that variable, or using a clear variable name. So I have encountered programmers who did both of these practices, and I would argue that if you had to choose, which you don't, you could always do both, clear variable name and a comment, but if you had to choose, then an unclear variable name is worse because you write that comment to explain it, but where you need to use that variable 10, 20, 100 lines later in your code, you're not going to be able to remember often what that variable actually was for. Someone who's reading your code, grading your code, working together with you on some code is definitely not going to understand what that variable means when it's used later. So if you choose a good variable name, that good understandable name follows along with the variable anywhere you use it. You probably also should include a comment that explains what that variable is, but if you had to choose between the 2 options, a clear variable name is really, really helpful. So overall, we want to think very clearly about when we are designing code, when we are coming up with code, to to address some problem, to do some task, to handle some need. We want to think through a very clear understanding of the problem, come up with a specification that tells us a little bit about what the program's uses will be like, design what the program will do, implement that design in a programming language, test it and debug it, redesigning where needed, and then continue to maintain the code if we want it to continue to be useful on into the future. And as you're writing the code, you can make it more maintainable and easier to test and easier to debug and easier to work on as you're writing it if you write understandable, readable code by using good names for things and by writing comments and documentation that goes along with your code.